Suppose you have a vibrator that generates a sinusoidal wave, and the vibrator is connected to a string with linear mass density that equals 16 grams per meter, and then and it generates with a frequency of 120 hertz. The length of the string is given to us 1.2 meter, and the other end of the string is connected to a certain weight, a mass. So the question is, what mass m allows the vibrator to set up the fourth harmonic? So which means we're also given that n equals 4. And to be clear, when we're saying the length of the string, we mean this one from here to this point, because that's where the standing wave is going to be created. And so you will have a wave looking like this. Now we want to ask a question again. What mass m is a question mark allows fourth harmonic to set up? That's the part A of the question. And then the second part of the question says, if we know the mass is 1 kilogram, we just hang 1 kilogram, then what standing wave mode is set up? To start solving this problem, let's see what we know about harmonics, especially the frequencies. So fourth harmonic frequency, if I want to write about the harmonics, that frequency equals 9 n times v over 2l, where n equals 1.2, 1, 3, 4, and so on. So, and in my case, I know n equals 4. Now let's devise a plan. How are we going to find the mass from here? So what I am thinking, that where could be the mass hidden? I don't know what is the wave speed, but one thing I know, that the wave speed is actually depends on the tension of the string, which is force of tension over the linear mass density. Okay, so again, we don't have the mass related, but I know that I can find the force of tension from the mass by, if I take a look at what force is acting on this weight. So it's the weight of the object hanging that will have the tension, provide the tension, force of tension, and the string. So, and then we know the tension everywhere will be the same. So I can say force of tension equals mg, and then the speed of the wave would be mg over the mu. Okay, now I can plug this v back into the equation of the frequency and solve it. So let's see. So we have the frequency equals 4 times square root of mg over mu over 2l. So one of the 2's will cancel out, and I have fl equals square root of mg over mu. Then let's square both sides. I will have f square L square equals mg over mu. From here, I can find the m equals f square L square mu over, it seems like I skipped the 2 here, so let me add that with the red. Okay, so that's divided by 2. So this would be divided by 4. And then so I have 4 I have a 4 G down here. Well, let's plug in the numbers and see what we will get. So that equals 120 hertz squared times the length is 1.2 meters. The linear mass density is 16 grams per meter divided by 4 times 9.8 meters per second squared, which will give me about 8,464 grams. Converting it to kilograms and rounding it will give me about 8.5 kilograms. Now let's go back and answer our second question. If we have m equals 1 kilogram, what standing wave mode is set up? Well, obviously, if we look the same analysis, we can write n equals 2LF square root of mu m over mg, and then all we need to do, plug in the numbers. So we have a 2 times 1.2 meters, 120 hertz, square root of 16 grams per meter divided by 1 kilogram, that is what's given to us, times 9.8 meters per second squared. Let's punch this into a calculator and we will get about 11.6, which is impossible. So by the way, when you plug in the numbers, do not forget to convert the 1 kilogram into grams or 16 grams into kilograms. It doesn't matter. So then you will get 11.6, which is not a whole number. So in other words, 1 kilogram object cannot set the vibrator standing on a standing wave. Thanks for watching.